Hi everyone, so this is a video on Step 2, 2021 and the very first question. For those of you who've been following for a little bit longer my channel, I know that I've switched from the map paper to the step. I'm going to go back to the map papers as well. This is typical me. I sort of end up doing 10 things at once. And because I'm doing 10 things at once, I end up doing quite badly. So sorry about that. But these just happen to be the questions which I was completing when I went on holiday. I've just come back from Mallorca. When I was under very rare moments when I had a moment to myself, this is what I got through. I've got through the first 3 questions, and I actually really like them. And normally step 2 I find punishingly difficult, but these were not as bad as they could have been. They're not easy, but they're not as bad as they could have been. Now let's take a look at it. Let's jump right in. Now before I start though, can I just say, please have a go at this on your own first. You'll get nothing out of it if you just watch me go through the question. Have a go at it, get stuck, see how far you get first, or you're not really going to understand why I've taken certain decisions. So yeah, you know where the step papers are. I think I'm going to leave a link in the YouTube just below the video for where I find these papers, but it's dead easy to find the map papers and the step papers. They're really transparent with the questions and the answers. Now this is just my approach as well. In fact, you're going to notice at one point I specifically say this is a stupid move, but I did it anyway, and I just like to show you what a typical answer looks like before we start polishing it and making it look really easy, because it's less realistic, isn't it? Okay, this one just says prove from the identities of cos of a plus or minus b that this is true. Now that's great because it's firstly giving you loads of guidance, but the first thing I thought when I saw this is this really reminds me of these formulas which I already know how to prove. Yeah, these formulas appear in the Edexcel formula book, and I'm sure in the other formula books under trigonometry in A level, and yet we hardly ever use them. Well, in fact, let me change that. You never need to use them in A level, yet they're there in the formula book. So you should be curious about these formulas anyway. I call them the factor formulae. I'm not the only person who calls them that. I call them the factor formulae. What are they useful for? Well, one example of when they're going to be useful is if you had to integrate something like sine 3x sine x, or sine 3x cos x, just so we can use that top one. Yeah, if you look, like if you had your a as 4x and your b as x, then you get now let's get this right. Is that going to give me sine 3? Yeah, sorry, let's make it 2x, so I apologise. If you made this 3x and x, then we're going to get 4x over 2. I'm just trying to make sure this turns out to be 3x. Oh, hang on. In fact, let me just actually solve it, because I'm doing so badly here. Let me solve the simultaneous equation. If we have a plus b over 2 equals 3x, whereas a minus b over 2 equals x, then we can see a plus b is 6x and a minus b is 2x, and therefore 2a is 8x, and therefore a is 4x, just as I said first, I think. And if a is 4x, b is going to be 2x. So just by instead rewriting this, because we can see 2 sine of a plus b over 2 cos of a minus b over 2 is going to be equal to that, I can now integrate this. And I know I've gone completely off topic here, but I just wanted to show you what sort of thing we use the factor formula for. We can now say that this is the same as a half, which you could of course place outside the integral, sine 4x sine 2x. That's the kind of thing you use it for, but it's like I say, it never really pops up in A level, but they pop up all the time in step, these formulas, so you should be aware how to prove them. Now essentially we're going to prove them. Now can I just point out as well, if you memorize this first answer immediately follows, yeah, because look at this. If we just look at the one with double cos in it, that's this one here, yeah, well we want cos a cos 3a, so, and we also, looking at this, we want cos 4a plus cos 2a here. Well, if I made a 4a and b 2a, sure enough I'd end up with 2 cos 3a cos a, which is exactly the result I'm trying to prove. In other words, if you know how to prove these, then you immediately know where this answer comes from. And that's the point I'm trying to make here. Now I do know how to prove these, and it's well worth knowing how to prove these. Let's firstly write down cos a plus b, which is of course cos a cos b minus sine A sine B. And then let's write down cos A minus B, which is cos A cos B plus sine A sine B. Now this is just one of these tricks you learn with a factor formula. The best way to derive them is just by adding these two together. So we're going to get cos of A plus B plus cos of A minus B equals 2 cos A cos B. And now look, we're really close to the answer. Firstly, we've got a product of two coses, yeah? The 2 we can move over to make a half on the other side. So we just need to make sure our A plus B equals 4A and our A minus B equals 2A. So if we choose wisely, and this is giving a massive hint here, let capital A equal 3A and capital B equal A, then we're going to have cos 4A plus cos 2A equals 2 cos A cos 3A cos A. And the result is there, yeah? So it's only a quick proof, but this is exactly how you would derive those formulas from the formula book, which we almost never use in A-level, yeah? It's exactly how we get these. Just to show you, I would probably, if I was going to prove these formulas, just as we've done before, let's say I'm going to prove this one, it's going to be exactly the same trick essentially, because you're going to get, and I'm just going to quickly show you it because I think it's an important thing that you need to be aware of. Cos of A plus B, essentially we're going to get exactly this answer here. If I can just write that down because it's obvious where that comes from. What you can do then, and I think I've got them all written down here, if you want to prove this result here, is, and we've kind of got the reverse of this result at the moment, we really have. If we were to say, let's actually pop it down like this and just having a look carefully at what I'm trying to prove. Let x equal A plus B and then y equal A minus B, and the letters are going to confuse you possibly a little bit here, but then A plus B over 2 is going to be, well, let's write this A now in terms of x. In fact, let's just add these together. Then x plus y is going to be equal to 2a, and so x plus y over 2 equals a. Yeah, perfect. And then if we, all I've done is I've added the equations together here to get that x plus y equals 2a to eliminate the b's. Likewise, we can therefore find, by plugging this in again, that b is going to be equal to, well, b is x minus a, isn't it? So we're going to have, and that leads straight away to, if we write that as 2x over 2, we're going to have y minus x over 2. And hence we've got this answer really, but just in terms of x and y rather than a and b, because we're going to have cos x plus cos y equal cos, 2 cos, sorry, of x plus y over 2 cos of y minus x over 2. And that is the same as x minus y over 2, because cos x is the same as cos of minus x, because it's an even function. Okay, so that's how you prove those formulas. I hope that makes sense. I've just done a very quick sketch of a proof there, and apologies that I've used like letters which are like completely the opposite to this. That was not my intention. I get sidetracked in maths all the time, and I like to suddenly talk about something which I wasn't planning on talking about. I wasn't planning on talking about that there. Anyway, back to the step question. Find a similar identity for sine A cos 3A. Well, if we use now these formulas, A plus B, it seems like, a fair guess that this is what we need to use next. And it's because if you think about how the right hand side is going to cancel, cos B, sine A cos B plus sine B cos A. If you think about how the right hand side is going to cancel, you're going to see why this is such a useful trick. Sine A cos B minus sine B cos A. Oh, my handwriting, it's so hard doing this online with a graphics tablet. Okay, so Same trick, add them together. So that's a secret to factor formulae, add together the compound angle formula, basically. And then the cheeky substitution is your friend. Okay, so 2 sine A cos B. Look at that, that's just like the shape of what we're looking for. We're looking for a sine A and a cos B here. And so this is definitely the way to do it. And now if we just, once again, choose wisely, let A equal, now we want the sine one to be the little one, so we're going to let A equal A this time and B equal 3A. Then we're going to get sine 4A plus sine 2A, oh no, sine minus 2A equals 2 sine A cos 3A. And as they want the result just like before, and also because sine is an odd function, you can take the minus out. Sine of minus x equals minus sine of x. Never forget the odd and even nature of sine and cos. It's really, really useful. That's going to give us sine 4a minus sine 2a. I don't know why I put that one in brackets, I'll be more consistent. Equals, oh, put the half over here, I suppose. Sine a cos 3a. And so that's how I did the first bit of this question. It is, if you know your factor formulae, this question is nice. If you don't know your factor formulae, you'll never get started because you need the second one as well. Even though I've told you the first one, you need the second one. Maybe not for this first bit actually, but certainly for part 2. Okay, let's do part 1. And if you don't mind, I'm just going to actually move this down here just so I can see. Sometimes you like a fresh page so you can actually see what's going on. Okay, right. So we're going to try and solve for cos x, cos 2x, cos 3x equals 1. And it seems obvious that that is no coincidence, and so we need to replace that with the cos x, cos 3x. And I'm going to move the 4 over onto this side, I think, first. Oh, no, I'm not actually. I'm going to leave it because I've got a half here times by the 4. So I'm going to get 4 times a half times by cos 4x plus cos 2x. Now I've replaced the cos x and the cos 3x. But I've still got a cos 2x lingering around, and it equals 1. And so what am I going to get here? Well, I'm going to get basically an expression which has cos 2x's in and cos 4x. But that's double angle formulae, and you can easily change cos 4x into cos 2x, because remember that cos 2a is 2 cos squared a minus 1, and therefore cos 4x is 2 cos squared 2x minus 1. And let's also let c equal cos 2x, because I don't know about you, but I get really bored of writing down cos 2x repeatedly. We're going to have 2c squared minus 1, that's from cos 4x, plus c multiplied by c equals 1. And now if we just multiply this all out, we're going to have a cubic. We're going to get 4c cubed, that's that one, and that one dealt with. Then you're going to get a minus 2c. Oh, and you're going to get a plus 2c squared. And then you're going to get minus 1 on the end after you've taken that over here. Let's just quickly check that. That looks all right to me. And you get to this familiar point in step questions where you've suddenly got a cubic to deal with. Well, how do we deal with cubics? It has to be factor formulae. It really does, you know, the guessing formulae. Now, I didn't find the guess very easy here, and I'm going to show you, like, this is, can I just point out, this is the silly way, yeah, when you don't check everything carefully, because I checked 1, I checked minus 1, no joy there, you know, I'm guessing at numbers which will make this equal 0 here. I guessed a half, no joy there. What I didn't guess was minus a half, or if I did, I was doing this, like I say, I was just outside Pizza Hut actually, waiting for a pizza when I was doing this question. And maybe I checked minus a half, maybe I didn't. But if I checked minus a half, I definitely got it wrong when I was doing the arithmetic. So what I started checking was known, known trig values, like, you know, root 3 over 2 and 1 over root 2. And it was 1 over root 2 where I had some success, yeah? But this is not the best way. You should check, if you check c equals minus a half, you'll be fine, yeah? But I didn't, and I just want to show you what a step question looks like when you don't get everything right first time, or you don't find the quickest way of doing it first time. So this isn't the quickest way, but this is just what I did. Let c equal 1 over root 2. Okay, 1 over root 2 cubed is 1 over root 2 times 1 over root 2 times 1 over root 2, which is 1 over 2 root 2. Yeah? Oh, sorry, people are messaging me. And 1 over root 2 root 2 times 4 is 4 over 2 root 2. Okay, then we're going to square, which is a half times 2, which is 1. Then we're going to do minus 2 over root 2. Look at that, that's the same as that. And then we get minus 1. That does equal 0. Hence, c minus 1 over root 2 is a factor. Okay, that's kind of like really nice to know, yeah? Now, there's lots of ways you can proceed once you've got one factor. What we could do is start thinking, well, the other two, the product of the roots, if you like, has to be equal to 1, because, you know, for cubics, if you've done some roots, product of the roots, that kind of stuff, you've got, you know, minus b over a is like, well, going to be equal to the sum of the roots. C over a is going to be equal to product pairs of roots, and then minus d over a is going to be equal to, so sorry, it should be equal to a quarter, I apologise. You could use that kind of approach. I think I'm actually just going to do, though, the approach where you basically do division by inspection. This is what I originally did, and it's not, once again, it's not necessarily the best approach. I'm not saying that, but I just want to show you what a messy step solution looks like. So I was thinking, right, okay, I need to come up with a quadratic which multiplies by c minus 1 over root 2 to make all of that. Well, clearly I need a 4c squared to make the 4c cubed. But that's going to give me minus 4c squared over root 2, which, you know, should we simplify this? Because 4 over root 2, well, that's going to actually be the same as 2 times 2 over root 2, which is, of course, root 2, yeah? It's, you know, it's worth doing that. Maybe you should just rationalise the denominator times top and bottom by root 2. You'll see that it's 2 root 2. So you're actually going to get 2 root 2 c squared, yeah? Now I want the 4c cubed, but I don't want minus 2 root 2 c squared. In fact, I'm going to add a 2 root 2 c to get rid of the 2 root 2 c squared. And that's kind of got rid of my root 2 on the c squared. But now I also need a 2c. It's supposed to be a plus. Cool. My handwriting. Let's make it a bit clearer. It's a bit of a weird way of setting out your working list, but this is what I'm going to do. This is what I did. Plus 2c squared. So now I've got that. Yeah. There are other easier ways I'm going to discuss right at the end why I should have just realised straight away that plus 1 over root 2 is going to be a root, because I need to get rid of my roots basically, and yeah, but I'll discuss that right at the end. Okay, plus 2c squared, and then I'm going to times all of that now by this. Now that's going to lead to, well, the root 2 is going to cancel with that root 2 there, so I'm going to get minus 2c, and then that one's going to become 2 over root 2, which is just root 2c. Okay, now what have I got here? Well, if you notice, I've already generated now the minus 2c, so that's kind of good, but I've got a minus root 2c, which I want to get rid of. So I'll put a plus root 2 here, and that will get rid of my minus root 2c, which I want to get rid of. And what I like about this method, it always shows you've done it right at the end, because I get a minus 1. And so I've actually managed to factorise it. And so I've got c minus 1 over root 2. And you might be thinking, that's a crazy method. And it's like, yeah, that's fine. It's just my way of doing things. It's sometimes silly. Plus c times 2 plus 2 root 2. And then plus a root 2 on the end. And so I've got it partially factorised into a linear and a quadratic factor. Now, if you think about it, right, we need, and this is the thing, this is what I should have realised before I did this. Firstly, as soon as I got one of my answers here, I was like, oh my god, I really should have done this in a much easier way. When we've got this and we're factorising it, essentially, I kind of guessed here a little bit at how this might factorise, like in terms of like 2c and 2c here and here. But then these two must multiply to give root 2, and everything's positive here. So I went with 1 and root 2. And sure enough, this works out right, because you're going to get a plus 2c, and then you're going to get a plus 2 root 2c, it all works out right. But what I immediately noticed then was, why didn't I try C as minus a half? I've made it way more complicated than this question should have been. By the way, this one ends up with giving you C is minus 1 over root 2 as well. And if you think about it, that makes a lot of sense, because we've got to eliminate the root 2's, because our original cubic, you know, didn't have any square roots in there. So when we multiply all those last numbers together, of course it should equal minus 1. And of course it does. So that's an easier way of looking at it. You know, we had like a minus 1 over root 2 here. We need two things to times to get minus 1. Well, clearly it was going to be root 2 and a 1. You know, seems pretty obvious now. Anyway, so what does that give us? That gives us cos 2x is 1 over root 2, or cos 2x is minus a half. That's the one we should have spotted earlier, and it makes it a lot easier, this question, if you notice that, but I didn't, and I just want to show you what it looks like when things go a bit wrong for you. Now, the last one gives you cos 2x is minus root 2 over 2, which is minus 1 over root 2. Yeah? And now we just, you know, use our known trig angles. Well, this is going to give us 2x is pi over 4, or 7 pi over 4, because that's how it works for cos, 2 pi minus first answer. This is going to give us 2x equals 2 pi over 3, or 4 pi over 3. And this is going to give us 2x equals, now we're going to have to do 3 pi over 4, or 5 pi over 4. You want to get good with knowing your trig knowing your trig angles, exact trig values. You've got to be good with that. And now we can just halve them all. Pi over 8, 7 pi over 8, pi over 3, sorry, 2 pi over 3, 3 pi over 8, 5 pi over 8. Done. That's the first part done. So apologies for all the waffle I've spoken in there, but that's how I approached it. And yeah, it's not the most efficient method, but I like to show when things go wrong as well sometimes, how even when it's going, you're not doing things the best way, you can get there in the end. Remember, it's your method and you own it, so you know, don't worry if you take the slightly scenic route to the answer. We all do that. We all do that, yeah? Okay, so that was part 2, and I think I've got that right. I think I've checked these answers, so I think that one's good. Okay, last part. Oh, by the way, whenever you're solving trig, and I just want to show you that this isn't a problem for this one, but you should always check that your solutions don't lead to, you know, contradictions, yeah? Now, what I mean by that is, in this one, it's not a problem, actually, because we haven't got any possible divisions by 0 occurring. With tan, it's different, yeah? Tan does actually equal, you know, tan x is infinite for certain values of x. For example, if you've just got tan x from minus pi over 2 up to pi over 2, tan of, you know, when you go tan of 90 or pi over 4, sorry, tan of 90 or pi over 2, you get undefined on your calculator if you press that. So you have to be careful when you're solving these kinds of problems, because you can get extraneous solutions. You have to check. So, you know, always plug your solutions back in. And if you plug any of those 6 back in, you should be fine, and they'll genuinely equal the answer. But on part 2, it's not like that. So, okay, let's have a look at part 2 first. What have we got here? Well, I suppose when I looked at this first, I got quite excited because I thought, I think I can see where they're going with this. We've got tan 2x, tan 3x, tan 4x. The shape looks quite similar to what we had before, quite similar. Let's just sort of like see if we can rearrange this into sines and coses, because that's what all our identities were about in the start, you know, so it's probably wise that we have everything in terms of sine and cos. Now, tan obviously is sine and cos, isn't it? Like, this is sine x over cos x. And I didn't actually write this line down, but I just like to show you it nice and clear. Sine 2x, sine 3x, sine 4x over cos 3x, cos 2x, cos 3x, cos 4x. And this is why actually we get the extraneous solutions at the end, because we're doing division by 0 essentially for some of these values. But anyway, if we take these over here and the cos x over there, then we get this nice little situation. Sine x, cos 2x, cos 3x, cos 4x equals cos x, sine 2x, sine 3x, sine 4x. Cool, that's what we get. Okay, so looking at that, and reminding ourselves what we already know, we know that 2 cos x cos 3x equals cos 4x plus cos 2x. We also know the equivalent one with sines, 2 sin x cos 3x is sin 4x minus sin 2x. Let's have a little think at what we've got now. So it's worth pointing out as well that we can, oh sorry, I've missed an angle in there, haven't I? Let's actually make, I do hate like when I miss angles, but we'll do it. Cos x cos 3x, that's better. Apologies for how messy my board work is here. What I'm thinking basically is we need to use the sin x cos 3x here with this one. So if I write that as cos 2x cos 4x and then multiply it by a half, obviously, sin 4x minus sin 2x, and then similarly on this side, if I use here the cos x sin 3x, well now I'm going to need this one the other way round, yeah? So let's see if we can just quickly work out the equivalent for 2 cos x sin 3x. If you want to work that out, the 2 cos x sin 3x is going to be equal to sin 4x plus sin 2x. Now you might say, well, why is that? Well, if you go right the way back to the start, when we were doing these, when we were proving these, if you had these the other way round, yeah, and this is what I actually had to think, if we had, because we've got sin 3x cos x this time, so if we let a equal 3a and b equal a, you get it the other way round, because you're going to get sin 4a plus sin 2a equals 2 sin 3a cos a. And that, of course, is exactly what we're looking for. So that's why I've done that. It's just basically a quick adjustment to the proof that you've done at the start. So that's what we need to do to make this a half sin 4x plus sin 2x. And then we've got these two to pop on the end, sin 2x, sin 4x. So that's starting to look pretty good because we've used the, the results which the question I think was obviously trying to get us to use. I'll cross out the halves because they're they're not really too important. Now, what have we got here? If we, I'm always thinking here as well. Look at where you're heading towards. We're trying to get a cos 6x or a sin 4x. Well, sin 4x is looking pretty good. Cos 6x, not quite obvious yet, but once you start multiplying this out, you can see what are you going to get here. We're going to get, in fact, let's put it onto this side. You're going to get, and it's, yeah, I'm going to leave it actually not multiplied out yet because it might be obvious anyway once I show you it. Sin 4x minus sin 2x. I'm thinking as well in my head here how I'm going to make sin 6x. Well, I'm thinking compound angle formulae, to be honest with you. Then we've got sin 2x sin 4x multiplied by sin 4x plus sin 2x. My handwriting's getting better, that's good. Equals 0, yeah? Now, they want to make a cos 6x, don't they? Yeah, that's what we really need to have. Sin 4x equals 0 is looking pretty good, but we need to make cos 6x. Now, if we look carefully, what's going to cancel here? You've got cos 2x, cos 4x, sin 4x. Okay, that's got no cos's in, that's not so important. And then you've got cos 2x, cos 4x, sin 2x. Then you've got a minus sin 2x, sin 4x, sin 4x, and a minus sin 2x. Let's actually write it down, okay. So we've got cos 2x, cos 4x, sin 4x, minus cos 2x, cos 4x. And this wasn't obvious to me, this bit, but it eventually dropped out nicely. Minus sin 2x, sin squared 4x, minus sin 2x, sin squared 2x, sin 4x. And that equals 0. Yeah. Now, you know, it's just not obvious necessarily how we're going to go about this, but let's see if we can puzzle it out. Oh, I've just I've just realised actually what I need to do. Can I just take that line about? This is often the case, isn't it, when you're doing step? I sort of do these live, and so I suddenly notice what I need to do. If I plug this in, just to cos 2x here, I'm going to leave the cos 4x outside, but I'm just going to plug in the cos 2x, multiply it through. I get sine 4x cos 2x minus cos 2x. Oh, yeah, hang on. Cos 2x. Oh, yeah. No. I'm going to try and make the cos one here. You know how, like, it's cos A cos B minus sine A sine B. Let me plug in, therefore. I'm just going to basically pull out the terms which I want. I don't care about the ones where it's cos 4x times sine 4x. I want cos 2x sine 4x or something like that. So I'm just going to rearrange this. Because look at this. Cos 2x sine 4x. But then I've got sine 4x. Yeah, in fact, I'm going to do the other one first. Let me just check I've written this all down correctly as well. This looks good. Yeah, that's it. I'm just going to rearrange this now. So I'm just glancing down at my notes here. I'm going to rearrange this so I've got sine 4x cos 2x. So I'm multiplying that one in there, and then I'm going to do the same over here, minus cos 2x sine 2x, and I'll leave the cos 4x outside for the minute, minus, and then I'm going to plug into here the sine 2x, so sine 4x is going to stay outside, but then I'm going to have sine 2x sine 4x, and then I'm going to have plus sine 2x sine 2x. And I'm just going to write down like that rather than squaring it, equals 0. And essentially what I'm thinking about here is how to make the cos 6x. Now, if you just write down quickly in a bubble somewhere what cos 6x equals. Cos 6x, if you're doing it in terms of 2x and 4x, well, it's cos 2x plus 4x, which is cos 2x cos 4x minus sine 2x sine 4x. Now, have we got that somewhere? I think we have, lurking around, because you've got, where is it? Now, let's have a look carefully. Where's your cos 2x cos 4x? Oh, it's here we go. It's right here, cos 2x cos 4x, and then the sine 2x sine 4x. Yeah, in fact, let's just factorize it out here. Yeah, I can see it now. It's sometimes more obvious what you're looking for when you write down the result which you're trying to end up with, because we know we need a cos 6x there. Well, let's actually, so I'm just going to take this back. Apologies for rubbing this out again. This was obviously the bit where I started to get just a little bit baffled, but I think I can see it now. So I want the cos 2x cos 4x, and I want the sine 2x sine 4x. So if I just have the sine 4x multiplied by, because that's times by both of those, cos 2x cos 4x minus sine 2x sine 4x. Lovely, because that's going to make me a cos 6x. And it helps let you know the answer here. It really does, doesn't it? And then if we write down the other terms, we're going to have then a minus sine 2x. And the minus sine 2x is in both of these. And that needs to be times by cos 2x cos 4x. And it's going to be, now let's get the sine button here. And then we're going to have the sine 2x multiplied by minus sine 2x sine 4x. Let me just check the sign on that. So what have we got here? Yeah, we're going to get minus sine 2x cos 4x minus sine 2x cos 4x. That's cool, that sign's correct. And then we're going to get plus sine 2x sine 4x. Now, do we get plus sine 2x sine 4x? No, that needs to be a plus like that. I think we're good now. Okay, let me just glance down at my notes and see. Yeah, my notes are exactly the same. Good, we've figured it out. So that was the most difficult bit, because now we've got sine 4x cos 6x, woohoo, lovely, minus sine 2x. Now what is this? That's going to be like 4x minus 2x, which is like cos 2x. It's cos minus 2x if you like, but cos minus x is cos x. And so we're going to get equals 0. And now we can rewrite that, of course, as a half sine 4x. And then sine 4x multiplied by cos 6x minus a half equals 0. Hence, sine 4x equals 0, or cos 6x equals a half. There we go. And looking very, very good. We're almost through an entire really nasty step 2 question. Of course, they're difficult. Right, if we just take this one first, 4x is going to be 0. Or pi, or 2 pi, or 3 pi, or 4 pi. That's always easy to deal with sine. And therefore x is going to be 0, or pi over 4, or pi over 2, or 3 pi over 4, or pi. Yeah, because we're only going from 0 to pi. Now, I'll talk about why some of these solutions aren't correct in the end. This one, we're going to get 6x, so inverse cos of a half, we're going to get pi over 3, 5 pi over 3, and then we're just going to be adding 2 pi, so you're going to get 7 pi over 3, you're going to get 11 pi over 3, you're going to get 13 pi over 3, and you're going to get 17 pi over 3. If you're wondering where I'm getting those values from, I'm just adding 2 pi onto that one, and then adding 2 pi onto this one, and onto this one, and etc, etc. Then just divide by 6, you're going to get pi over 18. I think all of these end up being solutions. 5 pi over 18, 7 pi over 18, 11 pi over 18. And look at this, 13 pi over 18 and 17 pi over 18. Cool. Now, why did I say some of these solutions don't work? Because you should always check at the end that you don't get any contradictions. Now, if you were to plug in, for example, pi over 4, yeah? Tan of pi over 4 is fine, but tan of 2 times pi over 4 is tan of pi over 2, and that's not allowed because it's infinite, and so the equation doesn't make sense. So it's worth just, so tan 2x fails here. So we cross that one out. Pi over 2 is the same, but in the original tan function. Yeah, it wouldn't work over there. So cross that one out. Tan x fails. 3 pi over 4, well, when you times that by, it's not the 4 pi, it's the 3 pi, because, oh sorry, it's a 2 pi, isn't it? Because when you do 3 times by, or sorry, 2 times by 3 pi over 4 is going to be 3 pi over 2. And as tan repeats every pi, and tan of pi over 2 is no good, tan of 3 pi over 2 is no good. So all three of those need to be excluded. And the reason that one's excluded is because tan of 2x, when you do 2 times that, you get infinity. And so all three of those are undefined. So you've got 0, pi, if I can just highlight my solutions at the end, you've got that one, you've got all of these. Those are no trouble at all. Do check them, convince yourself that they're no trouble, but I already have done. And that's the step 2 question 1 from 2021. Hope it was useful. I hope you enjoy my silliness sometimes as well when I get to the point in the question where it's a difficult bit and I start blathering. Yeah, apologies for that. Apologies for me doing it the silly way up here as well, but I just wanted to show you there that even if you do pick the least efficient method, you can still get it right. Okay, right, well done for listening, thanks for listening, and look out for my next video. All the best, bye bye.